Welcome back, students. In this video, we're going to take a short introduction into SN1 and SN2 reactions, which are types of substitution reactions. In substitution reactions, we're replacing one group for another. The leaving group is one group, and your nucleophile is going to do the replacing. So your nucleophile replaces the leaving group, so that now your nucleophile is part of your carbon chain and your leaving group is over here on its own. So NUC is the abbreviation for nucleophile. Sometimes people will abbreviate it as NU, right? Either one is perfectly fine, but this is clearly your nucleophile. The compound that has the leaving group on it is going to be your electrophile. A lot of times your leaving group is going to pull electron density its direction, leaving that partial positive charge on the carbon. Now, the electrophile isn't always called the electrophile. Sometimes it's called the substrate. And so the substrate is just another word for the electrophile in the reaction. And the substrate has two jobs. The first thing is when you have the, say, chlorine on here, the chlorine is going to pull electron density toward itself via induction. And remember that what that does is it leaves that partial positive on the carbon. So that makes the substrate the electrophile because now you have a partial positive and this is your electrophilic carbon. When the chlorine, which in this case is the leaving group, leaves, it takes on extra electron density. So it takes the electrons in this bond that I just highlighted in blue with it and allows for a new bond to form at the site that I've highlighted in yellow. So the substrate really has two important jobs. A lot of times your substrate is going to be an alkyl halide. Not all the time, but when you're first starting with substitution reactions, it's a nice, easy way to start students off, is to use alkyl halides as substrates. All the halogens, with the exception of fluorine, are going to make great leaving groups. When your leaving group leaves, the halogen, which is the X, plus these electrons end up going with it. We're going to end up utilizing the idea of primary, secondary, and tertiary again here, but instead of talking about it in the context of carbocations like we did in an earlier video, we're going to talk about it in the context of alkyl halides. Before we talk about primary, secondary, and tertiary, we have to recognize that the carbon where the halogen is attached, that's an important carbon. That's called the alpha carbon. Then next to that is the beta carbon. And then over here is the gamma carbon. And you're probably looking at the other side going, isn't that other one a beta too? Why, yes it is. So where the halogen is attached is your alpha carbon. One carbon away is beta, another carbon away is gamma, another carbon away is who cares because no chemistry is going to happen there. When we're considering primary, secondary, and tertiary, a primary alkyl halide will look like this, where you find your alkyl halide, you back up to where that alkyl halide is attached on the carbon structure, and you see, hey, that carbon has one other carbon group on it, so that makes this primary. A secondary alkyl halide will look like this, where you'll have, again, you find your halogen, X is the abbreviation for halogen. You back up to see where that halogen is attached, that's your alpha carbon. And then you see how many carbon groups are attached to your alpha carbon. There's two here, so that's a secondary alkyl halide. And then let's wrap up with tertiary. Now I have a halogen where I find my halogen. I back up, I see where that halogen is attached, that's my alpha carbon, and I count my number of carbon groups, 1, 2, 3 attached, and so that is tertiary. So make sure you can classify your alkyl halides as primary, secondary, and tertiary, just the same way that you classified your carbocations. What we're going to do is we're going to take some time to look at two different substitution reactions in detail. Right now, I just want to show you both of them as a comparison's sake. The first one that I've listed here is called the SN1 reaction. The second one is called the SN2 reaction. In the SN1 reaction, what is happening is your leaving group is leaving, you create a carbocation, and then your nucleophile attacks. If we go back to our arrow pushing patterns, this is step 1, where we see a loss of leaving group. And step 2, we see a nucleophilic attack. Because these are two separate steps, we call this a stepwise reaction. Whereas for SN2, notice how we have the loss of leaving group happening as the nucleophile is attacking. So here, both of those are happening at the same time. We have a word for that, and it's called concerted, when all the bonds are breaking and forming at once. You might be looking at your products here and thinking, you have the same products. Why does it even matter which mechanism I end up using? And the answer is you're not going to actually have the same products when you get these reactions. I just gave you an example that happens to give the same products. So you're going to want to take the time to watch the next two videos and really start to see the difference between substitution reactions that are SN1 and substitution reactions that are SN2. Let's wrap up. In this video, we gave a brief introduction to substitution reactions where we said that a nucleophile attacks an electrophile and a leaving group leaves. That electrophile is going to be a substrate. That substrate contains a leaving group. Halogens make good leaving groups, except for fluorine, which stinks. And we looked at how the mechanistic steps of loss of a leaving group and nucleophilic attack can either happen all at once, which we'd call concerted, or they can happen one at a time, which we would call stepwise. Thanks so much for watching. This is Katoni signing out.